Welcome back. I hope you had a nice weekend. My plan for today is I first want to go over your solutions, or however far you got to the permutation test hackathon, and discuss that. And then I also want to move on to talk about some modeling stuff from Module 7. So that'll be the main events for today. Also, assignment 5 is now live, and it's currently due at like at midnight on March 14th. But I'm going to update the official due date to whenever the last possible date for me to accept assignments is, which is usually like one day before grades are due. So I just need to find out when that is, and I'll let you know on Wednesday. But it'll be something like March 14th, but possibly slightly later than that. Before we get started going over the permutation stuff, permutation test stuff, does anyone want to bring anything up for discussion, comments, questions, concerns, etc., about any of the material so far? No. Okay. All right. So let me enable screen sharing, and then so I thought we could take some time to talk about or to see how far people got with the permutation stuff, test encryption breaking stuff. Does anyone want to volunteer to present what your group came up with, or walk us through? Would you like a few minutes to discuss in your groups to coordinate first? One nod and no other responses whatsoever. It's really helpful.
I'm just trying to run the thing. So
you're trying to run the thing.
Yeah.
Okay.
Like I'm just trying to run everything up until that point, like the decode and encode function, so that something is produced.
Got it. Do you want me to open up breakout rooms so you can talk as groups, or do you want to we could all stare blankly at our cameras for a few minutes? That's always fun. I'm seeing some nods. Okay. Oh, yes. Does yes mean the first option or the second option, or like, oh, multiple yeses? That's just so helpful. Yeah, like.
Breakout room?
Breakout rooms, sure. Why not? Okay, so I'll open up 3 breakout rooms. You can all choose your rooms. And then, I don't know, is 5 minutes enough? Do you want 10 minutes?
I think 5 is probably good.
Okay. I'll give you 5 minutes. Here we go. Rooms are open. See you in 5 minutes. All right. Hi again, everyone. So who wants to present first? Does anyone want to volunteer?
I'll go.
Cool.
Do I have screen sharing capabilities?
Yeah.
Okay. So at present, this isn't working, but I'll just generally describe the approach that we took. So the general idea is we decided to take a 2-step approach. And in the first step, we wanted to figure out, since there's sort of like a cyclical nature to the keys, we wanted to figure out the sort of appropriate shift of this long string of 1s and 0s so that we could then chunk it into things that wound up becoming letters instead of asterisks. And so that happens up here. And the approach that we took is we're basically going to make this list of the number of stars, and we're going to keep track of, for each shift of that long string of ones and zeros, how many stars are produced when we use the decode function on that list. And we're going to figure out which iteration of shifting that list along has the least number of stars, and then we're going to call that the like correct shift. So that winds up being in this variable min stars of 1, which you can see is used later on. And then the next thing we did was we decided to,
where do you compute n stars? Is that, potential, I see, okay. Potential offset dot count star, okay, great. Okay.
Right, so then the next thing is that we need to, now that we have the shift, we want to kind of roll through the possible options of sort of letter outputs, and that's kind of where we ended. So it isn't working yet, but the next thing to do is to kind of once you have the sort of ones and zeros converted into some string, the next thing to do is to kind of roll through that string and see when something is in this dictionary ing.
I see. Cool. Yeah. So ELT is like letter permuted or something, or circular shifted, or
yeah. So L is,
well, it'd be like a word, right? Or
yeah,
like a putative word. I see.
I think actually L is the list of strings that's produced by decode, if I remember correctly.
Yeah, great. Okay. And then what are you calling ing? Is the library, or is it like the English words library? Okay. Yeah, so yeah, so you're getting close there. So the first piece, finding the kind of initial offset, that will get you the minimum, within n times 8 of the true key, where you don't know n, and so now you have to find n. But then the second part, where you're like scrolling through to see where the real words are, this is the right idea. So you're on the right track here. Did anyone else like make additional progress beyond this point in terms of like, using looping through the possible words and seeing where the like valid and invalid words were, and using that to like kind of break the encryption faster? Or did anyone have a different approach for like, overall, or?
Our method was pretty similar, but I can share that if that would.
Sure.
That would be good. All right, so we took a pretty similar approach to the first bit, and for each possible key, we calculated basically the proportion of, we counted how many words in the string were stars and divided by the total number of words to get that proportion. And then for the legal English words measure, we sort of set it up in a big for loop with a word count. So it would split the string by spaces to get each individual word. And if that word occurred in the English word set, we would add 1 to the word count, and then the proportion there is the word count divided by the length of the string, or the number of words in the string. And then there was some debate about how much whether we should like weight these two goodness measures differently, or whether it made sense to just average them or add them. We ended up just adding them to see how it would work. And so we tested it with this, which is the encoded result for this is a test with the key 17.
Mhm.
And we correctly got that output.
Very cool. Yeah, that's awesome.
And
Yeah,
then
so
I
that,
think,
yeah.
we ventured a little bit into the permutation test, but I have to turn it over to Mijin to talk about that.
Sure.
Do you want us to cover that now?
Good question. Well, does anyone else have any other things to say about the like decrypt solution? Like, did anyone have a different approach? Did anyone solve it a different way? I guess I can't really see anyone's
Yes,
faces,
we
but
sort of did. Maybe you saw ours. Ours, we figured out there is a problem with ours, but
do you want to show what you have so far, or like
Yeah,
kind of where you
sure.
got up to? It could be
I
useful
can-
to talk about, if you got stuck in a particular place, it could be useful to talk through that.
Sure. Let me just make sure I have the right thing up. Yeah, cool. So, we have two parts. The first part checks the keys 0 through 7 to see which one yields the fewest stars. And then if, every time we get a better, like lower number of stars, we update the key and then that new minimum number. So to get like which position in 0 through 7 like lines up with the windows of the letters. And then after we have which position sort of lines up with the windows, we then test like given that starting position, either 0 through 7, intervals of 8. Here we're just like arbitrarily testing like the first 20 letters. But I guess we'd probably put that as a variable and do it so you could change it. But yeah, so then we using that use keys at intervals of 8 past that to see which one gives us the most like legal words. And it works generally. So like it will decode this. Oh, I have a print statement there somewhere, but it will decode this.
Did you try a different key just to make sure it's
yeah.
So like if you say if you encode the message with like an encryption key of 10 or something like that.
How does this work again?
So if you just put comma 10, that'll do it.
Hold on. Let me remove this. I don't know why that's there.
Ah, okay.
So there's, yeah. I'm not really sure.
Yeah, so you're getting the
first part is right.
So there the offset of 2 gets you within n times 8 of the true key, which is 10, because 2 plus 8 would be 10. But then it's so the missing piece now is like S is not a valid word, this and A are, and then testi, well, yes.
Yeah, I
That's
wonder.
Not, yeah, right. That
how many words finding? No, most words. Or I guess it's the same thing. So
Interesting.
that's an issue. It's only finding 3 words.
But that's one more than
Then is
there
here.
actually are. Yeah.
And yet there
Interesting.
are 4. There should be 4.
Well, there
So-
should be 4 in the
Yeah.
yeah. So it seems like maybe there are 2 issues. One is the maybe it's not assigning the best answer to the actual best answer you found. And then the second is maybe that you aren't like fully getting the optimization, or you're not, sorry, you're not like exploring sufficiently. It might be that 160 is too small. Like if you change that to like 1,000, it might work better.
No.
Oh, no, didn't. Okay. Okay. Okay, yeah. So this solution seems like kind of conceptually similar to the others.
Yeah.
Cool. Did anyone get this piece to work, or like, do you want to talk through conceptually how, like in more detail, or is there enough a sense of how you might solve it or want to solve it?
Something similar happened to us, I think, and I'm trying to remember what we did differently.
I think we were adding together the 2 like judgments, like the amount of stars was scaled like negatively, like the lower it was, the better it was. And then the word count was scaled, so the higher it was, the better it was. We were accidentally adding those together. So it was getting something in between the 2.
Interesting.
Right. Right. So it was just returning the wrong, it was kicking out the wrong key as having the highest score and returning.
I see. So I didn't check that carefully. Well, with any of, I assumed all those things were going in the right direction with all of yours. I didn't think to check that carefully, but that's definitely important. Yeah. So okay. So I mean, it seems like everyone had the right idea. There are a few kind of optimizations you might think about if you wanted to dig into this more. One is like so there are a few for loops in all of the solutions so far that you can swap out with for list comprehensions. So like for each possible key, you can count the number of stars in that key. So you could say something like, so if your message is like M, then you could say, like, have your function that, so M or decode M comma K dot count of stars. So get the star count for that, key K. And then you could say for K in, and then your list of possible keys. So you could start by setting the list of possible keys to just range of 8, and that'll test 0, 1, 2, 3, 4, 5, 6, 7. And then if you do like, so that'll tell you the star count for each of that'll give you a list with the number of stars for each possible key in the 0 through 7 inclusive range. And then if you say like, if you set that to some variable like counts, and if you say np.where counts equals np.min of counts, that'll tell you the key where those values are at their minimum. Does that make sense? Do you want me to screen share to show that? Okay, I'll screen, yeah. Okay. Okay. So, okay. Oops. Okay. Oh, I didn't write anything yet. Okay. So you could say like, get offset is some function of x or m, the message, and then you could say np dot where of I don't know if I can do it as a one-liner. Can't think of it off the top of my head. So, well, can't think of a clean way to do it off the top of my head. Okay. So we could say count equals decode mk dot count of star. That gives you the number of stars in the given decoded string for k in range 8. Okay, so that'll give you the number of stars returned for each possible, or each of the first 8 possible encryption keys. And then you could say return np.where counts equals np.min count, and that'll actually be a list. So then you want to return, or it's actually a list of lists, so you want to return the first element of it. So now we can say get offset of encode, this is a test of 4, and then it'll test the keys 0 through 7 inclusive, and so this should give us the correct key, but I have to import the NumPy library first. Thank you for reminding me, Mr. Tibbles. Yeah, my cat. Yeah, yeah. He's a very, very good debugger. Okay. Okay. There we go. Okay. Oh. So actually, I just want this to be an int. Let's see if that works. Yeah. Okay. Okay. So then that gives us our offset. And then next, we want to count the English words. So we could install this library, which, what is it actually called again? English, just English hyphen words. So English, is that spelled correctly? Yes, words. Okay. Great. All right, get rid of that. And then we could say, add that to our import statements. Import English words as ing. Okay. Now we could say, let's find the the positions of the valid English words. So we could say, or the invalid English words, actually. Maybe that'll be easier. So we could say def get invalid words of your decoded message. So we'll call it something else besides M. And then we could say, let's see. So return np.where, and then we could use another list comprehension. So we could say W in, or we could say W dot lower in ing dot, and then what are the options? Lower set. So that's the set of lowercase English words. So that's going to be a true false value depending on whether the word is in that set. For W in S dot split of the spaces. Okay, so that'll give us the valid words, but then we could get the invalid words by saying, is W not in that set? And then again, you have to do this like index of 0 to like return the actual list of indices because of weirdness with the np.where function. Okay, so then we could say like get invalid words of this is a test, and there will be, yeah, so it's nothing. But then if we like, you know, make one of the words invalid, it'll return that position. Then we could, you know, make this word invalid too. Make sense? So then, those are like loopless or effectively loopless ways of doing those two steps. And so it's, first of all, nice to think about, like, is there a list comprehension way of like implementing your functions? Because first, like Python can optimize how the loops are made when you write them as list comprehensions. Whereas if you like specify it as a for loop or a while, or even a while loop, although while loops are hard to make into list comprehensions, but, or possibly impossible. But when you write it as a list comprehension, Python can optimize that and run it a little faster at least. And also just makes your code shorter and cleaner and easier to maintain, et cetera. Okay, so the idea though is that now the next step would be to say, okay, the possible cut points of my message are going to be either in word 0, in other words, the first word, or word 2, in other words, the third word. And then I could say, let's read out the first word and then say, well, if I cut it at the first position, does that improve things? The second position, does that improve things? So I could say, like, is the word from like 0 to the end a valid English word? What about from 1 to the end or 2 to the end? And eventually I'll get to the word from 3 to the end is a valid English word. And so I know that one possible cut point that could increase the word count would be if I take these 3 asterisks and like draw a cut point there. So that'll increase my like cut count by 1. But then if I put those stars, so that's like, so I could loop through each invalid word and determine the possible cut points. And then for each of those, I could say, I have to say, like, what's the net benefit going to be? So if I move these 3 stars to the end in this string, that's going to make the last word an invalid word now. So I'm going to like increase the valid word count by 1 here, but decrease it by 1 here. So the net effect is 0. And then, whereas if I cut A from, like if I go up to the last index minus 1, then if I draw a cut point here, A will now become a valid word. And then if the star wraps around, well, it's actually everything after the star that wraps around. So now, but that's potentially okay, because now star is not a word, but that doesn't increase the number of, it doesn't decrease the number of valid words. And then test would get appended to test star, 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 this. And so that wouldn't be a word either. So that, but that doesn't decrease the number of valid words. So it doesn't mess anything up. So like cutting at this star here would like be better than cutting at this star here. Does that make sense? So to summarize, step one is say, what are the possible cut points, looking at just each word individually. And then for each of those cut points, and so to do that, you have to like step up from the beginning or back from the end of each word, each of the invalid words. And then ask like, at which possible places could I have cut this word to make it a valid word, if any? So if there are no valid cut points for that word, then it's just, none of them work. So you ignore that word and move on. But then you'll get a set of, across all of the invalid words in your list, what are the possible cut points? Now you have to convert those to like encryption keys to test out. And then those are the only keys that you need to test. All right, conceptually, does that make sense? Cool. That's how one might solve it relatively quickly. So there might not be many keys to test there. You can always come up with like an adversarial example for any given fixed algorithm. You could say like, we could design an example that's never going to finish. Like if I just put, a gazillion stars separated by spaces, I could make that list long enough that no computer would ever be able to chunk through that list. But, yeah. Anyways, but that would be a way to quickly solve this scheme in like the average case or something like that. All right. Cool. So I'm going to stop sharing. I guess any questions on the decryption piece? No? Okay. And then I think, Megan, you mentioned you had done something with the permutation test piece. Do you want to show, was it you, Megan? Or okay. Do you want to show what you came up with for that?
Yeah, actually, Mijin, did you want to take over the second half?
Oh, sorry, right.
Sure. Okay. Still, yeah. I would love to run by this everyone because I'm not sure if it's the right way to do.
Sure.
Can you see my screen?
Mm-hmm.
So this was the decrypt function part Megan presented earlier. So we didn't incorporate that idea of breaking things down 8 digits and make things faster. So we just basically deal with the entire string to solve this problem.
Got it.
So that's what we did. And then I think this, yeah, so this is the permutation test part. So basically I took big chunk of codes from decrypt function, because decrypt function in our design only spits out message and key, but we thought we need the entire goodness measure as a list from all the possible keys and possible text. So that's what it does in this part. So in the end, we get, so the goodness measure total list includes all the possible value of goodness measured from all the possible keys and texts. So that's what we have. So observed goodness measure is from the one one of what the text that we think the answer for the text. So that's what this variable has. And so this part is the one that we calculated from the entire goodness measure list. So the what was that? So this p underbar t takes in the possible length, given a possible length of x, which is the encoded string from the text that we use. We use the encode function to change to the encoded string.
Mhm.
And so this is one thing I'm basically thinking out loud because I wasn't sure this is the right way to go. But given that we only have finite number of possibility, which is, for example, if it's this is a test, it has finite number of one and zeros in its encoded string. So the number of possible answer that we can loop through in the permutation test is also finite. So we don't really need to set the number. For example, like I want to permutate like 1,000 times, for example, because it's already shorter than 1,000. So if we do that, so out of those finite number of possibility, and we calculated how many goodness measure of possible answers is smaller than the one that we got. So the answer with this is a test, and we got the answer, this is a test and the correct key, and it spits out, I think it was, when I tested, it was like 0.00085 or something. So it's pretty much significant low. But my question was, given that this scenario that we have on our hand is shorter than, I don't know, like the number of permutation we normally use in the permutation test, if this is the right way to go.
So there's a slightly more efficient way to code that particular line. So I pasted that into the chat. But I think you have the right idea here. So like, in other words, instead of doing length, so the GM total less than or equal to GM obs is a binary array. And then you're saying, where are those values true? And then how many of them are there? So that's the np.where tells you where are they true. And then length tells you how many elements are in that vector. A quicker way to do that is just to sum up the true false values, because true is a 1 and it is treated as a 1, and then false is treated as a 0. So the sum of that vector is the number of trues, which is going to be the same as the denominator of this line that you have here. So just, food for thought there. In terms of your other question about, but like in general, this is a reasonable way to approach this. In terms of your other question about like, do you ever need to specify the number of permutations? So if your set of possible keys is sufficiently small that you can test every one, then you can compute the full distribution, and you don't need to select a subset of those. But if I gave you 30 billion keys to test, then it's going to take quite a while to chunk through all the possible ones. And so really what you want to know is given how our knowledge of how the problem works, really what you want to know is the goodness value I'm getting out one of those, I happen to line up the offsets of the bytes correctly, or is it an actual greater than chance, greater than, am I doing better than that by also getting more words than I would normally expect? And so there, what you can do just as a first approximation is to say let me choose n keys at random from the total possible set, and then try just those keys. And I can test quite a lot of them. By chance, some fraction of those will happen to line up with the correct byte offsets. And then the correct key might or might not be in my test distribution, but that's fine. That won't change the p-value very much if I test enough of them. So then you want to know, like, is the key I'm guessing like better than the random, like all the random, or a good proportion of the random keys that I tested.
Yes, very good. Because like normally when we deal with the permutation test, we always have significantly a lot bigger than like the number of permutations we go through. For example, like 1,000. But in this case, the example that we used, which was this is a test, is subsequently it was significantly shorter than 1,000, for example, that you normally use. And then I think a lot result, and then it seemed very empty, and I wasn't sure if it's the right way to go. It makes sense, like you just explained.
Cool.
We definitely didn't go with the gazillion string ones and zeros
Cool.
as an example.
Yeah, so if you want more practice with, if you want more, so I want to, I think we've kind of, gotten what I was hoping out of this assignment so far. So I don't want to like belabor it too much longer, but if you want more practice with permutation testing, it's worth trying to like solve this efficiently, because that'll give you lots of practice with like, dealing with circular shifting and how do you account for that in like somewhat complicated bookkeeping scenarios and stuff like that. And then the example messages that I've included, like some of them will just take forever to solve if you solve them in the naive way. So it actually requires you solving it efficiently. Like your time on the Google Cloud will expire before you finish running it if you don't solve it efficiently. So, something to look at if you are interested in that stuff. Great. Yeah, so, and then the other thing I'd encourage you to think about is like, how can you apply these ideas to your own research? So like you have some quantity that you're interested in, like decoding accuracy with some brain data set or, some behavioral phenomenon. Then you want to know like, well, how can I quantify it? That's your goodness measure. And then how much would I expect to see that thing by chance? And that's your like, your goodness measure for each circularly shifted or shuffled data set. And then your permutation test is just the proportion of permuted values that are, have a higher goodness than your observed value. Okay. So I use permutation tests all the time. They're really ideal when you have a situation where like there's some set of assumptions that you probably should take into account if you knew statistics better and like remembered all the various tests you're supposed to apply to like make sure it's okay to do whatever the naive thing to do would be, like use a t-test. But the like quick way of dealing with those correctly without actually knowing like, all that stuff is just use a permutation test, and then your permuted data sets have to have the same properties as your original data. So if you circularly shift, they've got the same temporal properties. And then if they just regularly shift, it's the same distribution. So you know that like the same values went into your data set. You don't have to test for normality or anything crazy like that. Or like, are all the numbers positive? Is there some truncation issue? You don't have to test for that because your data set is exactly the same. And so it's just like a super useful tool. So that, okay. So in the, yeah, so there's other useful stuff in module 6 that I'd encourage you to take a look at, but I also want to make sure that we get to one of my favorite topics, which is building models. So I can really ramble on about this. So, feel free to jump in and interrupt with questions or thoughts. But maybe I'll just say a bit about building models and then we'll end, and then we'll pick it up on Wednesday. So I think one of the first questions that I often get when talking about models is like, what does it actually mean to model something? Like, what are we even doing when we're modeling? And the reality is there's no like one size fits all answer to what modeling means. But in general, it tends to mean something like one of several possibilities. So one option for what a model is a model is something like capturing some key set of attributes of the system or phenomenon that we care about. So for example, like a paper airplane could be said to model how a real airplane glides, in that like both use Bernoulli's principle like applied to the wings to keep the thing aloft. So that's one set of ways to model something. Another way to model something really means like prediction. So like you're predicting the future state of the system or the phenomenon. So for example, like a model of the stock market might make predictions about future prices, or like a model of people's heights and weights might allow us to predict someone's weight from their height, or vice versa. And then a third kind of way people talk about modeling, or what they mean by modeling, is something akin to simulation. So you're simulating some process. So in a simulation, the idea is to turn your assumptions about what happens when different elements of your system interact, or like how those interactions affect future states of the system, into a computer program. So like a simulation of the physical forces acting on a structure might describe like which parts of the structure, like if you have a bridge or something, might be likely to break or fail, or like how much strain like different pieces of the structure or the whole thing might be able to tolerate. So that's another like thing that's called modeling. Okay, that's what models. That's like what the idea of modeling is. So it can mean several things, all of which are kind of related. You're describing the behavior of a system, but there are nuances there, or different flavors of like what we're doing with the approach. Okay, first of all, are we good on that? Does anyone have any questions about that? Okay, for John. The second question I get most about what models are is like, what does a model look like? Like, how do you, like, when you have a model, what is that thing? So that the models tend to take kind of three potential forms, loosely speaking. So one way to model something, or one way you have a model, is you have a physical thing in the real world. Like a mouse brain can serve as a model of a human brain. Or like a small scale version of a bridge can serve as a model for the full scale version of the bridge. Sorry for the screams in the background there. Everything's totally fine. Yeah, don't worry about it. Okay. Let's see. A second type of form that a model can take is, most often like a system of differential equations. So equations that describe like how the different variables in a system change over time and interact with each other. So basically, like a model is a set of equations. And then the third kind of basic flavor that models come in is like a computer program that acts kind of like a hypothetical machine that tries to replicate some behavior in a real system. And then like, that's not necessarily fully distinct from the like pure equation models, because like a machine's behavior but is not necessarily describable using like differential equations or something similar to that. So for like the purposes of computational, psychology or neuroscience, people most often think of like the computational versions of models. So like the second two types of models, equations, or like little machines that are simulated with computer programs. And, you know, so that's what module 7 is really talking about when it's talking about models. The input to a model is usually some sort of data set, which usually takes the form of one or more tables of numbers that describe like known or assumed things that we think might affect the system that we're trying to model, or that we want to understand in the context of the system that we're trying to model. And then the output of a model is usually also one or more tables of numbers that describe the behaviors of the different equations or processes that are encompassed by the model. So like you put in some numbers and then you get out other numbers, and that's like the whole game. To me, when I built my very first computer model, that realization that modeling is all about describing or predicting tables of numbers was like simultaneously disappointing on one hand and also mind-blowing on the other hand. So it's disappointing because like I somehow imagined that building computational models had some sort of like magic Star Trek component to it, where like you scanned in every molecule of a system, and then like the rules of the universe, which maybe were like built into your computer system, somehow told you how the thing worked. And so like the reality is a lot more like mundane and simple than that. But then it started to blow my mind when I started to realize that like the magic Star Trek setup that I had thought of initially actually kind of is what modeling is. So it's not that you can scan in every molecule necessarily, but like if you think about how you'd actually represent that sort of data, you'd have to have like some way of storing the state of every molecule, which is probably going to be like a table of numbers or like a Python class, which is numbers. And then like, how would you represent the rules of the system? Like you'd need some sort of function, like set of functions that told you how the different elements of the system are affected by those rules, or like how different elements interact to change each other, produce new actors in the system. And like the whole trick is that computers can only tell us about the world in the first place by using and manipulating numbers. So for a computer, reality is numbers. There's no distinction for a computer or any way you could represent stuff on a computer between a thing in the real world and a measurement of that thing in the real world. Which because that measurement is ultimately just going to end up being a table of numbers. So when a number changes on a computer, if that number is attached to a label that you think is meaningful, like a brain state or a cognitive process, or like the level of strain on some part of a bridge, then it's as though reality itself is changing, or at least reality is filtered through the perspective of the computer. So it's like you're kind of creating a parallel universe, like a virtual universe, where you're essentially like a god because you know all the rules, you can control all the rules. But the fun thing is that then you get to press play on your made up universe and like see how all the different things that you put into your universe unfold into like some sort of complicated story. And like you may not have predicted how the story went before you actually ran the thing. Okay, so, oh, nice. Well, that kind of took us to the end of class. Did any of that make sense or maybe help frame what a model is? Great. Any questions? Maybe it's too high level at this point. So we're kind of out of time for today, so we won't have time to actually like start working with models. But like at least today, when I was thinking about this stuff on Friday at the end of class, I had wanted to start with the Hodgkin-Huxley model. There are various nice properties of that model. But in thinking about it more, I actually think it might be worth like practicing some of these intuitions before diving into that model. And so maybe on Wednesday, we'll do an exercise where I want to get you thinking about building models of things from your own research, because I think that'll also like be the most useful. So maybe you can start thinking about this for Wednesday, and then we'll talk more on Wednesday. Do some brainstorming about, like, first of all, what you might be interested in modeling. So like, one way to start thinking about that might be to like start thinking about like how you could frame how you might start to build models. Like what is possible to model, what is not possible to model, what are the distinctions, what makes a useful model, what would not be useful to model. And then once you think of that, so I want to discuss that more on Wednesday. Once you think of that, start to think about what things do you actually care about? Like, do you want to model like election outcomes, pandemics, how sea slugs locomote, predator-prey cycles, bird migration, why cats like jumping in front of Zoom cameras? Like, it could really be anything. And then maybe we can have kind of like a pitch session as part of that discussion. And then we could break off into groups and actually try turning some of our ideas into actual models. So I'm thinking that might replace the Hodgkin-Huxley model, but I'm happy to talk about the Hodgkin-Huxley model if people are excited about that. I don't want to deprive you of a nice model. Okay, great. So start thinking about that for Wednesday. And then let's see. So, and then also please just continue going through the Module 7 material that you think is relevant and interesting. That'll help also frame your thinking on this stuff. So a few of the most useful papers in that module are about different rules for building models, like what makes a good model, what makes a bad model, what is a model. I think there are lots of different perspectives. So I've now shared my perspective that I'm thinking of today about building models, but that's not necessarily the end of the story. So these other papers that I've posted, share somewhat overlapping, but not totally overlapping perspectives. And so it's worth getting exposed to that if you want to think about modeling. All right. With that, have a great rest of the day, and I'll see you either tomorrow in my office hours or on Wednesday in class. Take care, everyone.